All right. I welcome you all to the week nine's discussions session of the course Fundamentals of Conduction and Radiation. And continuing from where we left in the last week, as we saw that in this week we will start off with something which is known as which is another mode of another important mode of heat transfer, I would say. And this mode, which does not require any material medium for heat transfer to basically take place, is something known as radiation. And we will start off this week's discussion with introduction to this important mode of heat transfer, which is radiation, of course. And then we will proceed with radiation in the subsequent weeks. So, as I said, if you were there in the last week's session, or at least you saw the video of the last week that was shared in the website. From this week onwards, we will start off with radiation heat transfer, and the next subsequent weeks, I think we have 4 to 5 weeks left, and in the next subsequent weeks, we will be discussing concepts on radiation heat transfer and the associated problems that that are going to be present in these weeks. Of course, similar to the assignment problems that you are going to solve for radiation heat transfer. Okay, so this is basically the agenda of the next couple of weeks. We have finished conduction heat transfer. We discussed a lot. We started from the very basic Fourier's law of heat transfer, and then ended up to something which is known as solving conduction heat transfer equation using numerical method. For instance, we discuss how to solve the Laplace equation using a finite difference discretization, and solving an unsteady heat diffusion equation also using finite difference method, and looked into something which is known as the stability criteria for the explicit scheme using finite difference method, and so long and so forth. Okay, so as you saw, we started from the basic of Fourier's law. We extended our discussion into solving heat generation in heat generation in cylinders and slabs, and then we added our complexity, and finally we ended with the numerical methods, as we saw. So this is the same structure that we will follow in radiation heat transfer as well. We will be starting from the very basic of radiation heat transfer, something which is known as that we will see today. This is something which is known as the radiation fluxes. And these radiation fluxes, there are actually four important radiation fluxes. You can define your own fluxes, that is up to you. But in the literature, people generally define, people generally tend to associate radiation heat transfer with these four important radiation fluxes, which are the most basic things that you need to first understand when we learn radiation heat transfer. Okay, so then we will start off with this, and then we will increase our fundamental depth of radiation with something which is known as intensity of radiation, and associated with this intensity of radiation is the spectral intensity and the directional dependence of it. And thereafter we will look into, if we have time in this session, or else we'll look into it in the next session, is something which is known as the black body radiation. Okay, so once we are done with these three, which are, I would say, the most preliminary concepts of any course which involves radiation heat transfer, and once we are done with these things, we will look into radiation from real surfaces. And these are the things that we will see in the next subsequent weeks. And just to like give you a flavor, just like conduction, we will also see something which is known as the radiation network. You can also write the heat transfer between two surfaces or bodies that transfer heat by radiation in terms of the radiation network, as we will see. And also there is something which is known as the view factor analysis, and these are the things that we will keep for the next subsequent weeks of the discussion. Okay, uh, with this, I again welcome you all to this discussion session, and to the ones who attends the video and the discussion sessions, thank you very much. And if you still get time to watch these videos in your off time in through the YouTube links that are being posted in the website, if you find any like difficulties, or if you find any ambiguities, or any like questions that needs to be answered or needs to be addressed, you can always post it in the discussion forum. It's either me or like any of the course TAs will be very much happy to address your doubt. Okay, so having said that, let's get started with radiation heat transfer. And the first and foremost, as I said, we will be discussing the radiation fluxes, and then we will be solving an important sum involving these radiation fluxes, and then we'll go into the intensity of radiation, the spectral dependence, and the directional dependence, and so on and so forth. Okay, so when I say uh, when I say radiation fluxes, we first need to understand how radiation heat transfer basically takes place into, let's say, a body which is of any arbitrary shape, as I have considered here. So you can consider that in this body there could be an irradiation that is coming on from another source. This irradiation is basically described as, so this is something that we have already seen in the lecture series. So this irradiation is the rate at which radiation is incident upon a surface per unit area. For instance, if this is my surface, let's say if this black line is basically my surface, then the rate of radiation that is incident on this surface per unit area is known as irradiation. Now, based on this irradiation, there could be multiple possibilities that could happen. Some of this irradiation can get transmitted from this surface. This is known as transmission. Some of these could be absorbed into the surface. This is known as absorption. And some of these could be reflected from the surface, and this is known as reflection. So I could write that the net irradiation that falls on the surface per unit area, this can be written as, just by doing a simple energy balance, this can be written as, I won't say it's energy balance, because if you apply energy balance, there is also an emission going into it. But it's like, I can say that the net irradiation you can say then the net irradiation gets divided into into these three basically. That is that you can just interpret it like this. So the net energy that comes from the irradiation gets divided into the transmission, the absorption, and the reflection. Okay, so G can now be written as GTR, okay, which is the fraction of irradiation. So this GT, okay, so we won't say it's fraction, we'll define as a fraction in the next step, but we can say that it is the amount of irradiation after which the irradiation falls on its surface gets transmitted along the surface. This can be interpreted as the transmission, and we call it as GTR. So this G is the summation of GTR plus the absorption, which is GAB, plus the reflection, which is denoted by this, which is GREF. Okay. So now, so this is, of course, this is the flux. This is the first kind of fluxes that I am discussing, and this is known as the irradiation. Okay. Although I didn't write it explicitly. So as I said, there are four important fluxes that you need to understand, and one of the first fluxes is basically the irradiation. And as I said, irradiation is formally defined as the rate at which radiation is incident upon a surface per unit area. Okay. And of course, this irradiation can be transmitted, it can be absorbed, or it can be reflected. And that's why we have just written it in this form. Okay. So now what I can do is I can divide this entire equation by G. So it becomes 1 equal to GTR by G plus GAB by G plus GREF by G. Okay. Then this fraction, this GTR by G, is the fraction of energy that's get transmitted from the incident radiation. And this particular fraction has got a name, and it is known as tau. We call it transmittivity. Of course, since it's a fraction, transmittivity is always, so it has values from 0 to 1. It cannot be greater than 1, neither it can be less than 0. So this is known as transmittivity. We call it by tau. And the fraction of irradiation that gets absorbed in the surface is known as absorptivity. We call it by alpha. And the fraction that gets reflected is known as rho. Okay, so this is a very famous equation, that tau plus alpha plus rho is basically equal to 1. Okay, so this is something that you need to realize. I hope you have already seen this in the lecture classes, but this is just a recapitulation of doing the sums before doing the sums. So the first thing is that the transmittivity plus the reflectivity, that is the rho, plus the absorptivity is equal to 1. Okay. Now, if if my surface is opaque, okay, if the surface is opaque, which means, so if the surface is opaque, which means this transmission won't happen. This transmission won't happen now. This transmission, and then you know what you can infer is that your tau that we wrote here, that is basically the tau that we wrote here, this will, you know, go to 0, and then you can write, you know, if your tau basically goes to 0, you can write that the summation of your alpha plus rho is equal to 1, which means that your reflectivity plus absorptivity is basically equal to 1. Okay, so this is a consequence of the fact that you have an opaque surface for which your transmittivity is basically equal to 0. Okay, I hope like you are with me on this so far. All right. So this is something to do with the incoming irradiation that I said. Again, I repeat that the net irradiation that falls on a surface is basic. So it just has three possibilities. It can be transmitted, it can be reflected, and it can be absorbed. And from that, we came out with the conclusion that tau plus alpha plus rho is basically equal to 1. And if I have an opaque surface, I just have tau to be equal to 0, and then the summation of your absorptivity plus the reflectivity is basically equal to 1. Okay, all right. So this is something to do with the first flux, that is irradiation. And when I say flux, it has got a unit of watt per meter square, and that is something that you need to remember. Okay, now moving on, keeping this in mind, moving on to the second flux, which we call it as the emissive power. Okay, so let us now try to understand what basically is the emissive power. Okay, at least qualitatively and then quantitatively. So we understood that whenever there is a surface, there could be an irradiation that can be coming from a different source, and that irradiation is manifested by the symbol G, as we have seen. Okay, and but the very surface on which irradiation is being falling is also at a fixed temperature, or let's say is also at a at a finite temperature T. Okay, so this T in principle has to be greater than 0 Kelvin for emission to take place from the surface. So in with regards to its own temperature, a surface which is basically having a temperature T also emits radiation due to its own temperature. And that's why this emissive power, that is the second flux that we are considering, is basically the rate at which radiation is emitted from a surface per unit area. Okay, so try to realize that this emissive power has nothing to do with the reflected irradiation that takes place from the surface. It is just that on account of its own temperature, the body, or in principle the surface or the body, emits radiation because of its own temperature, and that emitted energy is known as emissive power. So these flux, so it's also a flux, and we denote this emissive power E as something which is known as the emissivity times sigma times T raised to the power 4. And this comes from a very famous law, which is known as the Stephen-Boltzmann law, okay, which says that the emissive power of the body is proportional to the fourth power of its temperature. Okay, and as you can see that if you have any temperature that is greater than 0 Kelvin, then you can appreciate that owing to its own temperature, the body will also emit certain radiation, and that radiation that is emitted, and that radiation flux that is emitted is known as emissive power. And from the Stephen-Boltzmann law, you can qualitatively say that this emissive power is proportional to the fourth power of its temperature, and the proportionality constant is reflected by this sigma, which is known as the Stephen-Boltzmann constant, and this sigma has got the value of 5.67 into 10 to the power minus 8 watt per Kelvin to the power 4. And of course, there would be a meter square because this E is basically the flux. Okay, so it's easy to remember the value of sigma. It is 5678. That is how you can remember. So it's just 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. Okay, so these flux that we now considered, okay, on account of the emission that takes place from its own body owing to the presence of a finite temperature is known as the emissive power. Okay, all right, so this is the second flux. The third flux that you need to understand is something which is known as the radiosity, and commonly in the literature this is denoted as J, and this radiosity is formally defined as the rate at which radiation leaves a surface per unit area. Okay, so now at least you can at least you can understand that the radiosity, which basically says that the net radiation which leaves a surface per unit area, has something to do with the combination of the emissive power plus the reflected irradiation. Okay, and just by simply doing an energy balance now, you can directly show that for an opaque surface, considering that there is no transmittivity or your transmittivity tau is equal to 0, you can show that for an opaque surface, your radiosity, which is, so this is thus obtained by just simply doing an energy balance on the body. You can show that your radiosity is the summation of your emissive power, which we will call it as E, or we have seen it is known as E, plus the reflected irradiation, so it becomes rho times G. Okay, and this is the relationship between the radiosity, the emissive power, and the irradiation. Okay, so this is also something that you need to understand. Oops, sorry. All right. Okay, I hope this is clear. So this radiosity can now be simplified as the emissive power, which for any generic body can be written as epsilon sigma t raised to the power 4, plus this rho for an opaque body can be written as 1 minus of alpha, where alpha is the absorptivity, times G, and this we have written it from this very equation. Okay, so this is one form of writing your radiosity in terms of the emissive power, the absorptivity times the irradiation. Okay, and let's say we name it as equation 3. We name it as 2. We name it as 2, and we name this very equation as 1. Let's say. Okay, and this is your 1A. Okay. All right. For the ones who just joined, what we were discussing is we were just starting the preliminary concepts of radiation, where we discussed the 4 basic radiation fluxes. We started off with something which is known as irradiation, and we saw that the net irradiation can be written as a summation of the transmitted irradiation plus the absorbed irradiation plus the reflected irradiation. And then after dividing with the total irradiation, we found out that the sum of transmittivity plus reflectivity plus the absorptivity is basically equal to 1. And for an opaque surface, this reduces to alpha plus rho to be equal to 1, where alpha is your absorptivity and rho is your reflectivity. Okay, this is the first thing that we saw. The second thing is something which we call as the emissive power, which we say that on account of its own temperature, a body emits radiation, and this radiation is quantitatively given by E equal to quantitatively given by the emissive power, which from the Stephen-Boltzmann law can be said that it is the emissivity times the Stephen-Boltzmann constant times the fourth power of its temperature. Okay. Then we saw something which is known as the radiosity, which is basically the net radiation which leaves a surface per unit area. And just by doing a simple energy balance on the surface, we saw that the radiosity is the sum of the net, so it's the sum of the emissive power to be precise, plus the reflected irradiation, which is rho times G. Okay, so remember this is true only for an opaque surface. Okay, and in radiation heat transfer and in this course, mostly we'll be dealing with just opaque surfaces, which means your transmittivity is basically equal to 0. Okay, and for an opaque surface, you can say that the radiosity, which means the net radiation which leaves the surface, is equal to the emissivity plus the reflected irradiation, and this is how it can be simplified. Okay, so we discuss up to here. I'll stop here for some time. If you have any questions on it, you can let me know. Okay, so these are the 3 fluxes. We are yet to determine one more flux. Okay, and the next is we will determine the last flux. I mean, as I said that you can call any flux as a flux. I mean, you can call any form of energy that leaves the surface per unit area as a flux. In that way, you can determine your own flux maybe. But in principle, in radiation, there are essentially 4 fluxes which we need to basically consider when we are dealing problems in radiation heat transfer. Of course, the first, second, and third being your irradiation, your emissive power, the radiosity, and the fourth flux that we will see now is something which is known as the net radiative flux. Okay, the fourth flux is not a different flux. It is just a result of the irradiation, the radiosity, and the emissive power, which says that so this net radiative flux, so you can kind of formally define it as the net rate of radiation leaving a surface per unit area. Okay, try to understand the difference between this net radiative flux and the radiosity. Okay, while the radiosity says that it's just the radiation which leaves a surface per unit area, the net radiative flux speaks about the net rate of radiation that leaves. So if we consider the net radiation that leaves a surface, this means that we basically need to subtract the irradiation from the radiosity. Okay, that is simple enough, because when I said the net radiation that leaves a surface, we need to account both the in and out cases, right? For instance, if we choose a control volume and we say that the net loss or the net change in mass, we just simply write it as m dot out minus m dot in. Similar analogy goes for energy or the momentum fluxes. In the same spirit, if we say that what is the net radiation that leaves a surface, it's simply the subtraction of the irradiation from the radiosity. Okay, I repeat, when I speak the radiation that leaves a surface, we simply call it as the radiosity. Okay, but if I say what is the net radiation that leaves a surface, I know, emphasize on the word net. Okay, it means that what is the energy that is going out minus the energy that is coming in. So the energy that is going out for an opaque surface is known as radiosity, that we have already found out. The energy that is coming in is basically the irradiation. So the net radiative flux, okay, is nothing but, as I said, it's nothing but, which we generally denote it as Q double prime rad. It is nothing but the difference between your radiosity minus the irradiation. Okay. Now, using equation 3, basically this equation, we can simply write down the radiosity as the emissivity times sigma times T raised to the power 4 plus 1 minus alpha times G. Okay, this is basically your J. Okay, and we have another minus G here, which means I can simplify this Q dot rad as epsilon sigma T raised to the power 4 plus G minus alpha G minus G, and this G's and G will cancel, which means I have this net radiative flux that leaves the surface as the emissivity sigma times T raised to the power 4 minus alpha times G. Okay. So this is the formal, you know, qualitative definition or more formal quantitative definition of the net radiation flux that leaves a surface. Okay. You can interpret as the emissive, you can kind of interpret as the emissive power minus the absorbed part of the irradiation, which of course makes sense, right? There is an irradiation, some of the irradiation will be reflected, and of course, due to owing to its own temperature, there would be an emissive power. So the net flux, okay, that is basically going out of the body, considering the fact that it's an opaque body, is basically the emissive power subtracted from your the absorbed part of irradiation. Okay, all right. I hope this is clear. But remember, this T that we wrote here, this T that we wrote it for the emissive power is actually the temperature of the surface, which you can crudely say is the temperature of the body. So this typically is denoted as Ts. Okay, so we will also just write it as Ts, following the same that is done in the literature. So this will be Ts, Ts, and this will be Ts. Okay. All right. So these are basically the four fluxes that you first need to understand when you are, studying radiation heat transfer. Okay. I'll stop here for some time. If you have any doubts on this, you can basically ask me. All right. If no doubts, uh, then we will. So this is the theory behind. So I think this you have already seen in the uh, lecture series, but just for a recapitulation, this is the theory behind these radiation fluxes. And then now what we will do is we'll solve a sample problem associated with these radiation fluxes. Okay. So we'll solve this problem. Yes. So there is a question. Okay, I'll see the question. So the question says that so it's a question. So it says that Kirchhoff's law states that emissivity is equal to absorptivity in thermal equilibrium state. Okay. Otherwise, the law of conservation of energy would be violated. Okay. If epsilon is equal to alpha, then why for the same material for x y for example white paint we have different values of emissivity and absorptivity. Are they material dependent property, or when we plot a graph between them at different wavelength, we get identical graphs? So these wavelength depend. So okay. Yes, actually, yeah. So I think I got your question. So you are just basically saying that if basically you use the Kirchhoff law, we say that emissivity is basically equal to absorptivity, but you are simply asking that yet for different for the same material we sometimes find different values of emissivity and absorptivity. That is typically because even if we that I simply did not say in the first, although I was planning to say it now when we learn something which is known as the spectral and the direction dependence, the more importantly something which is known as the spectral dependence. Okay. So what I think what Sanvi was asking is that even if we consider, yes, the Kirchhoff law the Kirchhoff law states that although we'll learn formally what exactly is Kirchhoff law in the next week, when we learn radiation from real objects, this is basically something that is radiation from an idealized object or a black body radiation that we will see shortly. But when we learn radiation from, ideal objects, we will learn formally what basically is the Kirchhoff's law. But the Kirchhoff law indirectly states that your alpha, which is the absorptivity, is equal to the emissivity. But I think the question is that even if this is for the Kirchhoff's law, yet there are some materials, yet like for some materials, I mean I would say not for some materials, in fact for all materials, you will find that your emissivity or absorptivity are indeed dependent on something which is known as the spectral dependence, which means that your properties like the emissivity, absorptivity, they are a function of wavelength. This is typically because when we consider radiation heat transfer, there is something which is known as a diffuse body. If we consider a diffuse body, it says that your radiation properties are independent of wavelength. And in that case, if you consider the same material, you will have the same value of emissivity and absorptivity across all wavelength. But in general, diffuse, in general, it is difficult to find diffuse bodies. Okay, so for instance, if I just pick a can of white paint, you will see that across different wavelength, your emissivity and absorptivity differs. That is typically because these sorts of material have spectral dependence. Okay, and when they have spectral dependence, you will see that the net radiation heat transfer that takes place is dependent on the wavelength that it is occurring. Okay, and that's why they are known as spectral properties actually. Okay, so that is typically the reason. For the same material, your radiation heat transfer can be different based on the wavelength that you are operating on. And similarly, you can show that it is also like dependent on direction. I was just I think I just stated it wrongly. For diffuse material, so if I have a diffuse material, it says that radiation heat transfer takes place in all possible direction. Okay, and if I say for a gray body, there is something which is known as a gray body, which means that it does not show dependence on spectral properties. And in case of gray bodies, you can argue that your spectral wavelength is basically equal to the total wavelength that we are kind of considering. Or sorry, you can just say that your spectral emissivity, for instance, is equal to the total emissivity. But this diffuse gray body are just an idealized body, idealized things in radiation. For instance, in general, you cannot have a diffuse or a gray body, and then you can say that your properties, for instance, the emissivity, the absorptivity, and all those things show dependence on the direction and on the wavelength. Okay, and this Kirchhoff's law is true for a gray body basically, and then only you can say that your emissivity is equal to absorptivity. Okay, I hope this is clear. Like, am I being able to like state it clearly? So, Sanvi, is it clear? Or do I need to repeat it again? Um, okay, all right. So, anyways, I was kind of like making a mistake between diffuse and gray. That I just said it wrongly basically. So I'll just repeat it again and I will try to make it more clear. So basically, when you consider radiation heat transfer, okay, there are two things that you now need to keep in mind when, but these things were not that important when we learned conduction and convection. Okay, so radiation heat transfer for a same, from a same surface is dependent on which direction you are basically looking at and in which wavelength range you are basically operating. The former, that is the directional dependence, okay, is no so it's also called directional dependent, of course, and the later, which is known as the wavelength dependence, it's known as the spectral dependence. Okay, now if we have something which is known as a diffuse body, okay, it just says that your radiation properties are independent of direction. Okay, that is one assumptions that we invoke, that if I have a diffuse body, we say that the radiation properties, for instance, the reflectivity or the emissivity or something, or all these things, they are independent of the direction. Okay, in the second sense, if I say that I have something which is known as a gray body, a gray body means that your radiation properties are independent of basically the wavelength. You can say that the let's say your spectral emissivity then becomes equal to your total emissivity, which means your spectral, so if we integrate basically your spectral emissivity along all the wavelengths for a particular property, if it's a gray body, you can argue that it's basically equal to the total emissivity. Okay, now if we invoke these two assumptions, that you have a body which is a gray body and a diffuse body, then you can say that your radiation properties are independent of both direction and your wavelength. Okay, so now, but in reality, we basically do not have that. For instance, if you have a can of white paint, you cannot just argue it to be a gray body, which means that along different wavelength, even if it's a white paint, you will see that your radiation properties would basically vary. And this Kirchhoff's law, that alpha becomes equal to epsilon, is true only for a gray body. Okay, And that's the reason why you see radiation intensities at different wavelength if you do not have a gray body with you. Okay. And similar analogies can be drawn also for diffuse body in the case of directional dependencies. Am I just clear with this? I mean, is it more clear now or? Okay. I think you got it, what I basically means to say. All right, that was a good question, in fact. But we will see more on something which is known as spectral dependencies and directional dependencies and the Kirchhoff's law in maybe towards the end of this session or in the next session. But yeah, this is basically how it goes. Okay, all right. Thank you for the question. It was a good question. Uh, yes, but I think for something if I will get that, I'll ask. Okay, so yes, I think. Yes, okay, sure. You just think it for some time, and of course, if you have any doubts, you can just feel free to interrupt me and ask your doubt, or you can also post it here in the chat, or you can also post it in the discussion forum if you feel like if you have any doubts in between these sessions that we have. Okay, I mean in between the week or like at any time. All right, thank you very much. Of course, that was a good question, but yeah, we will see more on it, and the things will be more clarified when we move into the when we move into radiation from real surfaces, basically. All right. Okay. So with this, let's try to solve one problem related to this radiation fluxes. So the problem says that the top surface of an L equal to 5 mm thick, aluminum plate is irradiated with G equal to 1000 watt per meter square. So the irradiation is basically given on this surface. Okay. And then it says that while being simultaneously exposed to convection conditions characterized by some heat transfer coefficient and ambient temperature, the bottom surface of the plate is insulated. For a plate temperature of 400 Kelvin, okay, it says that the temperature of the plate is basically equal to 400 Kelvin, as well as your absorptivity is 0.14 with emissivity 0.76. They are asking to determine the radiosity at the top plate surface. Okay, you need to find out the radiosity, then the net radiation heat flux at the top surface, and the rate at which the temperature of the plate is changing with time. Okay, so basically, it says that there is a surface which has some emissivity and absorptivity. There is irradiation on this surface. For instance, you can think of it like the irradiation that is coming from the sun. It have so apart from this irradiation, the surface is also losing heat to the ambient by means of convection, and it have an ambient temperature of T infinity, which with a heat transfer coefficient, let's say H infinity, whose value is basically equal to 40 watt per meter square Kelvin. Okay. Having said that, and given all the properties of this body, they are asking to calculate what is the net, they're first asking to calculate what is the radiosity. Oops. Okay. So they are just asking you to calculate what is the radiosity, the net radiation heat flux, and the rate of change of temperature of the body with respect to time. Okay. So we'll proceed we'll proceed it in a systematic way. And of course, I just didn't mention one thing. You can consider the rho, which is the density of aluminum, let's say, to be around 2702 kg per meter cube, and heat capacity as around 4949 joule per kg Kelvin. Okay, this is the data that you need to consider. All right. Having said that, can you now tell me how do we calculate the radiosity? Okay. Any ideas? So we just now saw how to basically, deal with it. Yes, E plus rho G, exactly. It's E plus rho G. That is exactly correct what Sanvi said. So basically, if we just do a simple, energy balance on this body, if we just do a simple energy balance on this body at steady state, you can uh, you can say that your radiosity, which I again repeat, it's basically the net radiation. So sorry. Psst. I think there is okay. Now I think it's fine. Yeah. Okay. So by radiosity, it means that the radiation which, so it's not the net radiation, remember, because if you speak about the net radiation, it becomes, so you need to consider the irradiation as well. So radiosity minus irradiation is basically the net radiation fluid flux. But if you just need to calculate radiosity, as Sanvi has rightly pointed out, it's basically the radiation which leave the surface per unit area. So it becomes the emissive power E, which you have stated, and the reflectivity times your irradiation. Okay, but we don't know reflectivity, right? So what do we need to do then? So how do we calculate this? So we don't know this rho, right? We just know the absorptivity and the emissivity. Yes, any ideas? So so it's a simple question because we have this alpha, which is absorptivity. Yes, yes, exactly. Rho plus alpha equal to 1, provided your transmittivity is equal to 0. Okay, so as you have rightly pointed out, we will use the fact that my alpha plus rho is basically equal to 1, which means that you are assuming it's an opaque body, assuming it as an opaque body, meaning your transmittivity is equals to 0. So now you can just say that your reflectivity is basically equal to 1 minus alpha, and in that sense, therefore your radiosity J is equal to E. So E, you can simply use the Stephen-Boltzmann law, which means it's emissivity sigma times T raised to the power 4 plus 1 minus of alpha times G. And now you just need to substitute the values. Your epsilon, which is your emissivity, it's given to be equal to 0.76. Your sigma is 5.67 into 10 to the power minus 8. And your temperature, that is basically the surface temperature of the body, is 400 Kelvin. This is given to you. This is your TS. So this becomes what? This becomes 400. Remember, this T, you need to convert it to Kelvin, because this emissive power is a non-linear function of T. So if it was delta T, let's say some T final minus T initial as we did in conduction, then even if your values are in Kelvin or Celsius, it doesn't matter. But here, since it's a fourth power of temperature, in order to do our problems in SI unit, you need to convert the temperature into Kelvin. That's a must. If it's given in Celsius, you need to convert it into Kelvin. That's it. Okay, so it was given that your T is 400 Kelvin. So this becomes 400 raised to the power 4 plus 1 minus alpha. Your alpha is given to be equal to 0.14. So it becomes 1 minus of 0.14 times your irradiation, which is 1000. Okay, and this is basically your radiosity. And just do the math, just do this multiplication. And if you do this, you should get your radiosity to be around 1963 watt per meter square. Okay, you can do this at your end and you will basically get this answer. Okay, so this is the first part of the question where your radiosity comes out to be around 1963 watt per meter square. All right. So you have determined the radiosity. That's the first part. Okay. All right. So now, can you now tell me, once you have determined the radiosity, what is the net radiative flux that leaves the surface? That's easy now, right? So what's the net flux? Yes. What would be the net flux? So you know what's the irradiation, you know what is the radiosity. The net flux is the net radiation heat flux is basically what? So we just now saw that, right? Yeah, exactly. It's J minus G, which means it's just the radiosity minus the irradiation. And this is obvious, right? Radiosity says what is the net. So sorry, radiosity says what is the, radiation heat transfer that takes place from a surface. or radiation flux that basically moves out from a surface, and irradiation is the radiation flux that falls on a surface. Okay, so the difference of this is basically the net radiation exchange that takes place between the surface. Okay, that takes place in the surface basically. So your Q dot red is the difference between your radiosity and irradiation. So this is basically 1963 minus 1000, of course with a unit of watt per meter squared that you know. So this will come around to be around 963 watt per meter squared. So this is your net radiation flux that leaves the surface. Okay. All right. Okay. So if this is the net radiation flux that leaves the surface, the third question now asks you that what if now the heat loss from the body is by radiation and also by convection, okay, then they're asking that what is the rate at which the temperature of the body is basically changing with time. So what they're asking is that once you calculate the net radiative flux, it says that the body also loses heat to the ambient by convection. And then now we have two mechanisms by which heat transfer is taking place from the body. One by radiation, for which the net radiation flux was 983, I think. How much? Yeah, it was 963 watt per meter square. And also there is a convective flux that leaves the body. Of course, we can calculate the convective flux because we know the ambient temperature and the surface temperature with the heat transfer coefficient. Okay, so once we know these two fluxes, they are simply asking us what will be the rate of change of temperature of the body with respect to time. Okay, any idea how we do it? How we basically calculate this dt by dt? Yes. Okay, I'll give you a hint. But how will we basically do? So what we'll do is we will choose this body as, I mean, we'll choose a control volume that that basically encompasses this body. Okay, and we will simply apply energy balance in this control volume. For instance, if I just apply, you know, this is my control volume, of course. This is my control volume, and if I just apply energy balance in the control volume, then it will say what? So the energy balance will say that the rate at which there is the net energy that is going out of the control volume, there won't be energy that is coming inside, that is not given in our question, and there is no heat generation taking place inside the body. So only the energy that is in transit from its surface is the energy that is going out, then that is E dot out, and this is equal to the rate of change of energy inside the control volume. Okay, and this is something that we get from the energy balance, if we apply the energy balance inside the control volume. And then I know that this Q dot out is basically equal to the summation of two fluxes. So it will be Q dot red plus Q dot convective, Q double dot convective, and the area will basically get cancelled actually from both these, from these sides and that side. That's why we'll calculate this per unit area, and I'll just not write down the area. And then this would be what? This would be this dECB by dt would be rho times C times its volume, times dt by dt. Okay, I think this is clear. Okay, we need to write down the area because this basically will take care of, so this will basically take care of the volume. So it's better we just write down this as the heat transfer area. So I'll just write it as AS for the time being. Okay, I hope this is clear. It's simply because, like, since we are considering volume here, so it's better to write down this as energy and not in terms of flux. So E dot out is basically the flux times the net flux times the AS, and this net flux is basically due to two things. First, there is radiation heat transfer taking place. We know this Q dot red, and there is also convection, which is Q CO and B. Okay, times this AS. So now what we'll do is we already know Q dot red. Q dot red is how much? We calculated it as 963, which is the net radiation heat flux that is going out of the body. Plus, there is also one flux due to convection, owing to the fact that the ambient fluid have a heat transfer coefficient H infinity and a temperature T infinity. So it can be written as H infinity times your ambient, so your surface temperature minus the ambient temperature. Okay. And then what I will do is I will write it as rho C times V by AS into dt by dt. Okay. Where this V by AS, as we have seen multiple times, this is basically your characteristic length of the body. And then you can simply just plug in the values now because you know all the values. So your dt by dt is basically minus of 963 plus H infinity is given to you. Your H infinity is how much? It's 40 times your surface temperature is how much? Your surface temperature is 400 minus 30. Okay. This is your flux due to convection and radiation divided by rho C L, LC basically. Okay. So that's all right. So this LC now, your characteristic length would be the length up, within which there is a appreciable change in temperature. So your LC would basically be equal to this L, which is your 5 mm in this case. So you just need to substitute values. So it will be dt by dt equal to how much? So it's going to be minus of 963 plus 40 into 400 minus 30 is 370 divided by your density is 2702 times your specific heat, which is 949 into the length, which is 5 mm. So it basically becomes equal to 0.005. Okay. So just do this, and okay, if you do this, it's just that you just need to do this simple. Okay, I think we are doing it correctly. It seems, yeah. Yes, I think it's correct. So you just need to calculate this. If you just calculate this, you will end up your dt by dt as around minus 0.378 with a unit of Kelvin per second. And that's it. Okay. So all right. So I think this is clear on how did you calculate the rate of change of temperature on the body. So I repeat, why did we basically do this? That is typically because, like, for this body, we have two modes of heat transfer that is taking place from the body. One, the radiation flux that we already calculated, the net radiation flux, and the convective flux, owing to the fact that the body is now exposed to a fluid having a heat transfer coefficient H infinity and a temperature T infinity. So these are the energies that are basically going out from the control volume, and that's why we wrote it in E dot out as the sum of these radiation and the convection fluxes. And because of the fact that these are the energies that is going out from the body, the energy inside the control volume, that is basically the body itself, and the temperature inside the control volume, to be precise, the temperature will now decrease with time basically. And then you can simply write it as the rate at which the energy is changing inside the control volume to be the density times the specific heat times its volume multiplied by dt by dt. And you know everything. You just need to plug in the values to basically calculate how your rate of change of how basically the temperature, what is the rate of change of temperature with respect to time of this body. Okay. So this is the third part, and we have done the third part. So I hope it's a good question on the radiation fluxes, and also the combined effect on how to deal with the combined effects of radiation and convection. Okay, so I hope this is clear to you. Uh, I'll stop here for some time again. Like, if you have any questions, you can ask, or else like we'll move into something which is known as the yeah. So we'll move into something which is known as the intensity of radiation, and then we'll look into something which are the spectral properties and things like that. Okay. So if you have any doubts on this, you can ask me, or else we'll proceed with the next discussion. I hope this problem is clear. How did we solve this? Yes, I agree. It was a simple yet important problem. Uh, Basically, because we learned how to deal with the both radiation and how to calculate the net radiation flux from a surface, and the fact that there is also convection taking place uh, as a mode of heat transfer in addition to radiation. Okay, I'll stop here for some time. If you have any doubts, you can ask me. Meanwhile, I'll just come in 2 minutes by filling my mark. All right. Uh, let's see if there are any questions. Okay. Okay. If no questions, then we'll move into something which is known as intensity of radiation and how it is related to something which is known as the emissive power. And then we'll solve a problem related to it as well. Okay. So we'll start off with this. All right. So the next agenda for discussion. So we have finished discussing on the radiation fluxes, which are the most preliminary things that you need to know while you are, dealing with radiation heat transfer. The second thing, and the second most basic thing, is something which is known as the radiation intensity. And as I said, we will see something which is known as the spectral dependency you know, in this session. So so this is something that we wish to discuss now. So as I said, let's get started on this. So just 1 second. All right. So so what I was trying to say is something which is known as the radiation intensity or the intensity of radiation. And this intensity of radiation is defined as something like this. This is again that you saw in your lecture series. It's just a recap of what you guys just saw. So this intensity of radiation, also sometimes it is known as spectral intensity of radiation, typically because this intensity of radiation that we will see now depends on it depends on the wavelength that we are currently operating on. So that's why we call it as the spectral intensity of radiation. And the spectral intensity of radiation, it is generally denoted as I lambda. Lambda suggests that you so basically lambda suggests that the property is dependent on the wavelength, and we'll denote it as I lambda E, which means it's the spectral intensity of the emitted radiation, and it is formally defined as dq. I'll tell you what dq is, divided by dA1 cos theta times d omega times d lambda. Okay, so this is the mathematical description or the mathematical definition of the spectral intensity of emitted radiation. Okay, And it says that, so it can be defined as this lambda I lambda e. It can be defined as, so I'll write it down. So it is the rate at which the radiant energy okay is emitted at the wavelength lambda in the theta phi direction per unit area of the emitting surface normal to this direction per unit solid angle about this direction and per unit wavelength interval okay so per unit wavelength interval d lambda about lambda. All right, so it's a big definition actually on the intensity of radiation, and this is typically how the intensity of radiation is defined. I have taken this definition from the book of Incropera. So you can easily find this in in the textbook of Incropera. But yeah, so this is how the intensity of radiation is defined. Okay, so let's have a look at it. It says that the spectral intensity of emitted radiation, okay, defined by I lambda e. Again, I said that this lambda, which I say, I think there is a connection issue in my laptop. I don't. I think you can. So can you just see my screen? Can you see my screen? Can you? Okay, yeah. Okay, thank you very much. Okay, so the spectral intensity of emitted radiation, it is defined as I lambda e. Okay, lambda meaning that it's a property that is dependent on wavelength, and we call it the spectral properties. E means it's the intensity of the emitted radiation. That's why you call it as E. It is defined as the net radiant energy, that is dq, that is emitted at a particular wavelength lambda, because it's a spectral property, in the theta phi direction, which means that as I said, the radiant energy that is being emitted, the net radiant energy to be precise, that is being emitted at a particular wavelength is also dependent on which direction is this radiant energy being emitted. Okay, that is, it's a function of the azimuthal and the zenith angle, as you can see from this figure. Basically, because we kind of deal in, so direction in radiation, we kind of deal it with respect to the spherical coordinate system, and that's why we are calling it as in the direction of theta phi. Again, meaning that this radiant energy that is being emitted from a surface is a function of the wavelength. It's also a function in which direction basically we are looking. Okay, and that's why it says that emitted at the wavelength lambda in the theta phi direction per unit area of the emitting surface normal to this direction. For instance, if this is my surface which is emitting radiation, and I look and basically I seek to understand what is the intensity of radiation at an angle theta in this direction, to be precise. So the area that I need to consider is the area that is normal to this direction theta. Okay, and that's why this becomes dA1 cos theta, and that's why it is written per unit area of the surface normal to this direction. That is typically why this cosine of this theta comes into the formula, and it is It is not only there, it is per unit solid angle, and that's why this d omega comes into the picture. For instance, if I have a sphere, so basically a solid angle, I think you guys know this, a solid angle is denoted as d omega or dw, whatever you say. It is equal to the dan times divided by r square, where dan is the fictitious, it can be thought of as the fictitious area normal to the direction in which we are looking at the radiant energy, okay, divided by the distance between the source and the object, okay. And this ratio is known as the solid angle, okay. I think you guys are aware with this. For instance, if I have a sphere, my solid angle is just sine theta d theta d phi, okay. And that's you can easily calculate it out at your end. So so again it's calculated per unit solid angle, okay, about the direction, and the per unit wavelength interval d lambda about lambda. So this is exactly the definition of the intensity of radiation. Okay, I understand it's a big definition, but it is just how it is defined. Okay, so any doubts on this? First of all, in the definition of this intensity of radiation, I again repeat, it's the radiant energy that is being emitted from a surface having area dA1 in the direction normal to this surface. That's why this cos theta comes in the picture, per unit solid angle per unit wavelength. Okay, about the wavelength interval d lambda. Okay, and this is how this intensity of radiation is basically defined. Okay, so what we will do is we will just write this dq by d lambda as something which is known as dq lambda. So what I will do is I will just write this dq by d lambda as some dq lambda. Okay, and where this dq lambda, so it's just a simplification, we'll just write this dq by d lambda as some dq lambda, where this dq lambda is the rate at which radiation of wavelength lambda leaves dA1. Okay, and it not only leaves dA1 and passes through DAN. Okay, DAN is basically the area that is subtended by the solid angle. Okay, so this is the definition of dq lambda. And now if I want to write this dq lambda in terms of the spectral intensity of emitted radiation, it simply becomes I times lambda e. This I times lambda is a function of its wavelength, it's a function of theta, and it's a function of phi, times dA1 cos theta, okay, d omega or dw, whatever you say. So this is typically the relationship between the radiant energy that is emitted about a wavelength lambda and the spectral intensity of radiation. Okay, I hope this is clear. All right. Okay, so I hope this is clear to you, and I hope I'm not making any mistakes. So we'll just name this equation. Maybe we'll name this equation as some equation 1. This is as some equation 2. Okay, where I said that this d omega, where this d omega is the solid angle, is basically the solid angle given by your DAN, which is the area subtended by the solid angle divided by the square of the distance. Okay, now let's look into something which is known as the hemisphere. So there is something which is known as the hemispherical emissive power. Okay, there's something which is known as the hemispherical emissive power, which means, so try to understand what this means. So this relation is just a relationship between the radiant energy, or kind of the spectral emissive power, and the intensity of radiation in general with respect to the normal area, that is the area from which the radiation is being coming, and the solid angle d omega. Okay, now if I say what is my hemispherical emissive power, it's like, okay, now I have a surface d having an area dA1, and I have an kind of an arbitrary hemisphere that basically encompasses this surface. Okay, now if you ask me, if I now have a, let's say, arbitrary and a fictitious hemisphere that basically surrounds this surface, and if you ask me now what is the what is the spectral emissive power that comes from this surface dA1 onto this hemisphere. Okay, and then I can tell you that the spectral emissive power, which it's basically called the spectral hemispherical emissive power, typically because we are kind of like calculating it on the hemisphere. Okay, and we will denote it as E, and this is basically equal to your intensity of radiation I lambda E, which is a function of theta and phi, and of course it's a function of lambda, times your dA1 cos theta. And now can you tell me what will be this d omega, because now it's a hemisphere? Can you tell me? See, I hope this is clear. So this is a generic relation which relates how my emissive power, this dq lambda, is also interpreted as the spectral emissive power. It's just the same. Okay, it's just a relation which says that how my spectral emissive power is related to the intensity of radiation in terms of the area from which the radiation is coming from, and the solid angle. Now if I say you that for a special case, I need to see what is the emissive power that is coming from dA1 on a arbitrary hemisphere having spherical coordinates r, theta, and phi. Okay, so then can you tell me what will be this d omega based on the fact that this is a hemisphere? Remember, I already said that the solid angle that is subtended by a hemisphere or a sphere onto a differential area dA1 is equal to your sine theta d theta d phi. Okay, this you can basically prove. Okay, so by using spherical coordinate, you can actually prove that your solid angle is basically your sine theta d theta d phi. Okay, I'll not prove here for the sake of time. I'll just not prove here, but you need to understand that if you have a hemisphere or a sphere, the solid angle that is subtended from its surface to a differential area is sine theta d theta d phi. Okay, so now if we basically want to calculate what is the hemispherical emissive power, we need to now integrate this equation along the zenith angle and along the azimuthal angle. Okay, so your azimuthal angle, which is basically your phi, this integration, can you tell me from where to where your phi should vary if we want to calculate the hemispherical emissive power? So it's like, so I'll just simplify your understanding. So it's like I have a surface. Let's say this is dA1, just how the surface that we kind of drawn recently. So let's say this is the surface dA1, and I now need to find out what is the hemispherical emissive power from this surface dA1. So I will just draw a kind of hemisphere like this. Oops, just didn't become a hemisphere. Oops, not like this. Maybe I'll just draw it by hand. Okay, maybe like this. And then, you know, maybe this is your r direction. Okay, and if I just project this is your theta direction, this is your phi, and this is your theta direction. Okay, so now can you tell me for this hemisphere from where to here, where to where your theta should basically vary, and from where to here your phi should basically vary to calculate the hemispherical emissive power? Can you just give it a try? So forget about the hemisphere. If it's a sphere, how does your zenith and the azimuthal angle vary? Yeah, 0 to pi by 2 for theta, exactly. No, will it be pi by 2? Yes, it's true. It's true. Yes, it will be 0 to pi by 2. Exactly. Yeah. So 0 to pi by 2 for theta and 0 to 2 pi for your phi. Okay. So you have rightly pointed out. So it's going to be 0 to 2 pi for the azimuthal angle, that is for the phi, and 0 to pi by 2 uh, for in the zenith angle. And in that way only you can basically generate. So you can speak about it like it's a generating angle for a hemisphere. If you want to generate a hemisphere, your zenith angle should vary from 0 to pi by 2, and your azimuthal angle should vary from 0 to 2 pi. If you want to generate a sphere, your zenith angle should basically vary from, or your polar angle should basically vary from 0 to pi, and your phi should basically vary from 0 to 2 pi. Okay, this is how you basically get a sphere and a hemisphere. Okay, so now since you are interested in the hemispherical emissive power, okay, your theta should basically vary from 0 to pi by 2, your phi should vary from 0 to 2 pi. Okay, now if you calculate this, so if we just calculate this, your hemispherical emissive power is nothing but an integration of 0 to 2 pi and a 0 to pi by 2, sorry, times your I lambda E, which is the intensity of radiation, times theta times phi, sorry, intensity of radiation, which is a function of theta, phi, and lambda, okay, times your dA1 cos theta, and of course, then we have this sine theta d theta d phi. Okay, now we'll just do a simple thing. Instead of calculating the emissive power, we'll calculate the emissive power per unit area of dA1, which now it becomes the flux. So we'll just write it as, so remember this emissive power is a function of lambda as well. So we'll just write this, as E lambda by dA1, which now becomes the flux. It's kind of the hemispherical emissive flux. Okay. And this is equal to integral 0 to 2 pi, integral 0 to pi by 2, the intensity of radiation, I lambda E, which is also a function of theta, phi, and lambda, times cos theta, sine theta, d theta, d phi. Okay. And this is your expression for the hemispherical emissive flux. Okay. So try to understand, this is the hemispherical emissive flux that is emitted from a area dA1, okay, in terms of the intensity of radiation, in terms of the spectral intensity of radiation to be precise, and projected on a fictitious hemisphere. Now I'll ask you an interesting question here. Why did we consider a hemispherical surface and not an entire spherical surface? Can you tell me? We could have just considered also a spherical surface, right? So why are we so interested in a hemispherical surface and not on a spherical surface? So I'll just repeat. So all this business that we did, that relating the emissive power with that of a hemispherical, emissive power, uh, because I also stated that the intensity of radiation is dependent on the direction and as well as on the wavelength, and that's why we considered an arbitrary hemisphere that is basically surrounding this area dA1. My question is, why didn't we consider a sphere and instead we considered a hemisphere? Okay. Meanwhile, we'll just name this. Maybe we'll name this equation as some equation 3. Okay. So yeah, any answers or any like any guess why didn't we consider a sphere? Okay, think about it and I'll ask it in the next class. What's the answer? I'll give you some time to think about this. Okay. So now we will see something that is interesting. So so try to now understand that if dA1 is a diffuse emitter, as I said, then that if the area from which it is basically emitting basically emitting the flux is a diffuse emitter, okay, then I can simply write that my I lambda E, which was a function of theta, phi, and lambda, it now becomes it now just becomes a function of just this lambda, which means that if I have a diffuse emitter, then my property does not become a function of the direction. It says that in all direction it emits radiation. It just means that it emits equal amount of radiation in all direction, which means that the intensity of radiation does not become a function of the direction we are considering. And this is the property of a diffuse body. Similarly, if I say if it is a gray body, then I would say that this intensity of radiation or any other property, they does not become a function of the wavelength. But here it's a diffuse body, which means it's not a function of the direction. Okay, I hope this is clear. So if DA1 is a diffuse emitter, then my intensity of radiation or my spectral intensity of radiation is not a function of direction. So I can write this I lambda E as just a function of its wavelength lambda, which means I can now bring this I lambda E outside of this integral, because I lambda E now no longer becomes a function of theta and phi. And that's why I can simply write my, Q lambda double prime as I lambda E, which is a function of lambda, and this is integrated upon 0 to 2 pi and 0 to pi by 2, okay, cos theta, sin theta, d theta, d phi, okay. Now can you tell me what is this value? Can you tell me? Just do this integration. So you will see that this simply, so this integration is doable, right? First integrate it in the theta direction, then this integration is just a 2 pi times this 0 to pi by 2 cos theta sin theta d theta. And how you do this integration? Just multiply and divide by 2. This 2 times of cos theta sin theta would basically becomes cos to theta, I'm sorry, sin to theta, and then you can just do that integration, okay. But anyways, if you just do this integration, this will simply turn out to be pi. Okay, so you can show that for a diffuse body, your spectral emissive flux is basically equal to the spectral intensity of radiation, I lambda E, times pi. Okay, this is a very famous result that I think you guys have at least seen that if you have gone through this week's lecture series. Okay, so this is true, but remember this is true for a diffuse body only. It is simply because for a diffuse body only, you can say that the intensity of radiation, so in general, the intensity of radiation is a function of the direction, that is the theta phi and the wavelength lambda. But for a diffuse body, you can say that this intensity of radiation no longer becomes a function of theta and phi, because it's the very definition of diffuse body which says that the properties are now not dependent on direction. And you can then say that your intensity of radiation is just a function of wavelength, and that's why you can bring this out of this integral. And if you just do this integration, which is a fairly straightforward integration, you will see that this simply comes out to be pi. So for a diffuse body, the spectral emissive power is equal to the spectral intensity of radiation times pi. Okay, so this is one of the important relations that you guys need to understand. Okay, now if I just do one more thing, if I just integrate this equation uh, for all the wavelengths, that means I just integrate this I lambda E lambda, so this would be just pi, and this is d lambda. Then you can say that your emissive power now, that is the emissive power per unit area, which is Q double prime, is pi times your intensity of radiation. And this is true if you integrate it for all the wavelengths. basically. Okay. So this is also one of the important results that you guys need to understand. All right. So this is something to do with this. So this is the theory behind something to do with the intensity of radiation, the very definition of intensity of radiation, and what are basically spectral properties and what do we mean by a diffuse body. Okay. So I'll stop here for some time. If you have any doubts, you can ask. You can basically ask me. Okay. But think about this: why did we calculate this hemispherical emissive power in order to come up with the fact that your emissive power is pi times the intensity of radiation? Okay, why didn't we just consider a sphere around this? Okay, all right. I'll stop here for some time. If you have any doubts, you can ask me. So actually, I just didn't wrote here explicitly. This q double prime is actually, so you are integrating this along all the wavelengths. So it is 0 to infinity q prime of lambda d lambda, basically. Okay. So this is also known as the total hemispherical emissive power, to be precise. Okay. And if you want to define, and formally, if you want to define, this is the rate. Okay, just for the sake of clarity, this is the rate at which radiation is emitted per unit area at all possible wavelengths. Okay, this is precisely the definition of hemispherical emissive power. Okay, but remember, this is true for a diffuse body only, which means your properties are independent of the directions. Okay, I hope it is absolutely clear what we are doing. So this is the beauty and the complexity of radiation, is that now if you are studying radiation, you also need to think that your properties are also a function of the wavelength in which the wavelength you are operating. It's also a function of the direction. Now, for simplicity, we already saw that if it's a diffuse body, your properties are independent of the direction, but yet they are a function of wavelength. And if you want to get the total property, that is the basically the total, let's say the total emissive power, you need to integrate the spectral emissive power along all possible wavelengths. That's why we integrated it from 0 to infinity. Okay, to get the total hemispherical emissive power in terms of the total intensity of radiation, I. Okay, I hope this is clear. So is this clear or not? Can you just give me with an yes or a no, or like, do you need any explanation on this? Any more further explanation on this? Um, yes. Okay. Okay. Thank you very much, San. Okay, so if it is clear, so let's first think what did we learn. So we started off with the radiation fluxes. We saw that what kind of fluxes do we need to deal with when we study radiation. So once we knew these fluxes, we saw that these fluxes are just not mere fluxes as we just deal it with conduction and convection, because of the fact that the properties in radiation or the fluxes in radiation, they show dependence on the direction as well as the wavelength. Okay, so if we have a property that is dependent on wavelength, it's called a spectral property. For instance, the emissivities, okay, and let's say the emissive power, the intensity of radiation, all these things are a spectral quantity because they show dependence on the wavelength. And we have also seen that these quantities show dependence on the direction as well. For instance, if I have, let's say, a surface, the radiant energy or the emissive power of this surface, okay, which so basically so you can just think of it as the emissive power that comes out from this surface is dependent on which wavelength do we need to calculate this emissive power. It is also dependent on which direction are we calculating this emissive power. But we have seen that for a diffuse body, okay, which means that the properties of this surface, if this surface is a diffuse surface, the properties of this surface is independent of direction, which means if I, let's say, want to calculate the emissive power, I don't need to think about which direction do I need to calculate the emissive power, typically because the properties are now not a function of the of the direction. And by direction, we have brought about the concept of this hemispherical, fictitious hemispherical, kind of a cavity. And I ask you the question, why do you need to consider a hemisphere? We will you think about this question. And my simple question is, why didn't we just consider, let's say, a triangle, or let's say a cubical cavity, and why did we just consider a hemisphere in order to describe the direction? Okay, you think about that. But in any ways, I mean to say is that if I now have a surface which is emitting radiation in all possible direction, yes, the properties are now spectral properties because they are dependent on the wavelength. But still, if it's a diffuse surface, then the properties are not a function of the direction, and in radiation it's not a function of the zenith and the azimuthal angles. Okay, and then in that case we can say that, okay, wavelength as a direction. Okay, so I think there's, okay, I'll come to this, but yeah, so I'll just finish it. So I just said that if it's a diffuse surface, we can show that the total hemispherical emissive power is equal to the pi times the intensity of radiation. Okay, so I think there is, okay, so yes, I think there is an answer to it. So Sanvi says that we know the body emitting has to be a function of wavelength as well as the direction. Okay, that is true. Hence, the radiation needs to be emitted in a direction that can be observed. A spool sphere radiates in all direction, but only the radiation from a hemisphere can be observed. Yes, that is exactly the case. Okay, I understood what you want to say, but typically, that's the answer. But typically, it's a very common sense question. Typically, because see, it's a surface which is basically radiating in all possible directions. Now, if I place a sphere, it cannot capture the radiation that is coming out from the bottom surface, because we don't have anything that is known from the bottom surface. All I am saying that it's just this exposed area A1 which is emitting radiation in all possible directions. Okay, so it's just that if I want to capture the net radiative flux that is coming from DA1, it is sufficient for me if I consider if I consider a fictitious hemisphere that will capture all this radiative flux that is coming from DA1. And that's why we consider this as a hemisphere, basically, and not a full sphere. Okay, so yes, your answer is correct. But yeah, that's the reason that's why we consider it as a hemispherical emissive flux, and that's why it is known as a hemispherical emissive flux, to be precise. Okay, all right, so we'll end this discussion by just solving one problem that is associated with this intensity of radiation. And the problem statement is something like this. I want you guys to read this problem once, and we'll just end this discussion today by just solving this particular problem. Okay, so it says that consider a small surface area of A1 having, so area of this A1 is given, which emits diffusively. So remember, it's a diffuse emitter now, which means that the property is in that means the emissive power is independent of the direction, and it have a total hemispherical emissive power E1 of this much. Okay, and what they're asking now is, given that A1 is a diffuse surface having a total hemispherical emissive power of E1, they're asking at what rate is this emission intercepted by a small surface A2, which is basically this, okay, which is oriented as shown. So they're asking that if A1 is a diffuse emitter and it is emitting radiations in all possible direction, okay, then what is then what is the rate of this emission that is coming from A1 is being intercepted by A2, which is placed at this particular orientation from A1. Okay, that is what they're asking. Okay, the orientation is given, and finally they are also asking what is the irradiation G2 on A2. That means what is the radiant energy that is falling on A2 that is coming from A1, basically. These are the two things that they are kind of asking. Okay, and this is so basically what we need to find, we need to find number one, Q12, okay, that is the rate of energy I mean the rate of radiant energy basically. I mean the radiant energy that is coming from 1 that falls on 2. Okay, given the orientation of 2 that is completely given to us, and number 2 the G. I mean G meaning the G2. That is what is the net irradiation on on this uh, this surface A2 that is coming from A1. Okay, so any idea how will we proceed with this problem? So we looked into this, right? So can you tell me which expression do we need to use? So it's just that we just need to use this expression, right? We just need to use this particular expression, which relates how the intensity is related to the emissive power, basically. Okay, so we just need to use that expression. I hope you are clear on uh, you are at least clear in this point why basically we are using that particular expression that we just now derived. Okay, yes, okay, all right. So this Q12, I mean, from the above equation that we saw, can be written. So this Q12 is basically the net radiant energy, or you can interpret as the emissive power that is equal to the intensity of radiation that is coming out from 1. In general, it is a function of theta and phi. In general, I would say, times dA1 cos theta d omega, but it would be 2 1. Because when I say it's the solid angle, it means the solid angle that is basically the solid angle subtended by the receiving area on the on from that is the solid angle subtended by the receiving area on the emitter's surface, basically. And that's why I'll write it as 2 1 and not 1 2. So you need to understand this difference. And now, luckily, they have said this so they have basically said that this IE1, they have said that it's a diffuse emitter, which means that your intensity is not a function of the direction. That means it's not a function of this theta and phi. So you can simply write that this IE1 times pi is equal to the you know is equal to the emissive power emissive power of the body 1. And then you can simply write this as IE1 equal to E1 by pi, where E1 is nothing but the emissive power of the body 1. Okay, so therefore your Q12, that is the radiant energy that is leaving from body 1, that is intercepted by body 2, is equal to your emissive power of body 1 by pi, typically because your body 1 is a diffuse emitter. That's why you can just use this expression that we just now derived. And this is equal to, then this multiplies by your area of dA1 into cos theta. This would be 1 cos theta 1 into d omega of 2 1. Okay. Now we need to calculate, for getting this Q12, that is the first task that we need to do. We need to calculate what is this d omega 2 1. That is what is the solid angle subtended by 2 on 1. So can you tell me any idea what is the solid angle subtended by this on basically 1? Given that we know what is the orientation of this object 2 from the orientation of 1, can you tell me what is this d omega 2 1? So d omega 2 1 can be simply written as dan, that is the normal area. Okay, that is in the direction of this A2 divided by r square. Okay, and this dan of 2, this can be written as, if you basically look at the geometry, it can simply be written as A2 cos theta 2 divided by r2 squared. Okay, and this is exactly your d omega of 1 2. It's simple, right? Because see, this normal is in this direction, so your dan is basically this area. Okay, and this is what is the solid angle that is being subtended by this area. So the normal area with respect to this A2 is going to be A2 cos theta 2 divided by this direction, from the definition of solid angle, of course. Okay, so now you know these values, right? A2 is known, cos theta 2 is known because this angle is known, and r2 is known, this is 0.5. Everything is known. So your your d omega 2 1 just simplifies to a2 cos theta 2 by r2 square. Okay, where everything is known in this part. And cos theta 1 is also known. Cos theta 1 is known because your theta 1 is 60 degrees. So this just become cos of 60 degrees. Okay. And your dA1 is also known. Your dA1, because your dA1 is just A1 itself, which is 10 to the power minus 4 meters square, which means you know everything, right? You know everything of this from. Can you tell me what is this E1? How to calculate this E1? Yes. I mean, E1 is also given. Okay. E1, luckily, this total hemispherical emissive power is also given to be 5 into 10 to the power 4. So it's like everything is given to us. We just need to substitute the values. So let's do this. So your Q12, oops. So your Q12 is equal to your E1, which is how much? Which is your E1 is 5 into 10 to the power 4 divided by pi. Your A1 is given to be equal to 10 to the power minus 4 times cos theta 1. This cos theta 1 would become cos of 60 times your d omega 2 1, which is a solid angle. So this would be A2. Your A2 is given to be equal to 5 into 10 to the power minus 4 times cos of 30 divided by R2 square. Your R2 is 0.5, so it becomes 0.5 squared. Okay, so that's it. That's it, guys. So this is just Q12, and if you just calculate this Q12 would come out to be equal to 1.378 into 10 to the power minus 3 watt. That's it. This much is the radiant energy that is leaving surface 1, and it is intercepted by surface 2. That's it. So you just do this. So you just do this calculation. You should end up getting this number. Okay. See, so how did you do this? We started from the basic definition of the radiant energy emitted by a surface 1 that is intercepted by a surface 2 in terms of the intensity of radiation, and we saw that if it's a diffuse body, you can simply relate the intensity of radiation as pi times, the intensity of radiation times pi is basically the emissive power. So you can just write this in terms of the emissive power for a diffuse body, and this basically is nothing but the hemispherical emissive power. Okay, it's the same thing. When you say emissive power, it indirectly means it's the hemispherical emissive power only. Okay, for a diffuse body, of course. And since we know what is the value of the hemispherical emissive power, we know this E1, and all those things comes from the fact that there is an area which is normal to this direction, and the solid angle that is subtended by the area 2 on the area 1. Okay, so once all those things are known, it is sufficient for us to basically find out what is the radiant energy, okay, that is leaving from one surface and it is intercepted by the other surface. Okay, and this is basically the answer. Now, there is one more thing, one more interesting thing that they're asking. Can you tell me what is the irradiation G2 on A2? If we know the radiant energy that is leaving one, so this is the radiant energy that is leaving surface 1 intercepted by surface 2. If that is the case, can you tell me what is this G2? That is the irradiation on surface 2. Can you give it a try? It's very simple. You just need to think about it. What is the definition of irradiation, basically? Yes, any suggestions? How do we, given that we know what is the energy that is leaving surface 1 is interpreted by surface 2, can you tell me what is the irradiation on surface 2? Given that we know the energy that is falling on surface 2 and the area of surface 2. That's the hint. Yes. That's simple, right? Because so what is the definition of irradiation? Irradiation means the radiation, that is the radiation, that is the flux, that is the radiation flux that falls on a surface. Now, the radiation flux that falls on surface 2 should come from surface 1, right? And we already know that what is the amount of energy, what is the amount of emitted energy of surface 1 that falls on surface 2. This is basically this. So the irradiation on surface 2 is nothing but the fraction of energy, or the amount, or it's not the fraction, but it's the amount of energy that is coming from surface 1 is falling on surface 2 divided by, if I just divide it by the area of surface 2, it just becomes the irradiation on surface 2, right? So uh, this is simply 1.378 into 10 to the power minus 3 divided by, remember this should be the actual area of surface 2, because if the flux, it should not see, if you just write it A2 times cos theta 2, this is wrong. It should be just A2. Okay. It is simply because now, see when we calculate, the radiant energy leaving a surface, we calculate it with respect to the projected area, and that's why this cos theta term came into the picture. And similarly, when we calculate the solid angle, we say that it's the angle subtended by the area which is in the direction normal to the direction of the emitting radiation onto the surface from which the radiation is being emitted. And that's why this cos theta again come into the the formula of the solid angle. But when you are calculating irradiation, it's just that how much is the radiation energy, how much is the radiant energy that is falling on a surface per unit area of that surface. And that's why it becomes A2 and not just A2 cos theta. And you know what is A2? A2 is nothing but 5 into 10 to the power minus 4 meters square. And your irradiation would just be equal to 2.76 watt per meter square. That's it, guys. So this is the amount of irradiation, okay, that is falling on surface 2. Of course, that is coming from surface 1. Based on the fact that your surface 2 and surface 1 are, oriented in this manner. Okay, so is this clear? Basically, so couple of things you need to keep in mind. First, how do you calculate the radiant energy that is leaving surface 1 and intercepted by surface 2? That is simply equal to the intensity of radiation. Okay, I would say it's the spectral intensity of radiation, but here, like, let us consider it for a given particular wavelength, and that's why we have omitted this term. So remember, it is more accurate to write if we just write it as q1 to 2 lambda, and this just becomes I lambda basically. But remember, if we are not writing lambda, we are considering that this is true for a given wavelength. Okay, and that's why we are just not writing lambda in this case. But it should, but since but it's more customary, and it's more of a good practice if you also define it, that is this is true for a given wavelength lambda. Okay, now in this question, since it is not since we are just calculating it for a generic wavelength, we just stated that the amount of energy that is leaving from surface 1 is equal to the intensity of radiation that is coming from surface 1 times the normal area of surface 1 dA1 cos theta multiplied by the solid angle that is being subtended by this surface. Okay, and then what we did is, it was given that it's a diffuse emitter, so we said that this intensity of radiation is now the emissive power of 1 divided by pi. Okay, and that's what we did. We just substituted this. In fact, this is the hemispherical emissive power. Okay, and then what we did is we just calculated this q12, which is the radiant energy that is leaving surface 1 that is falling on surface 2. Okay, because we know what is the solid angle that is being subtended by surface 2 on 1, and all the areas is just known to us. Now once that is known, what they have asked us is to calculate now the irradiation on surface 2. So it's very simple, because we know what is the radiant energy that is leaving surface 1 and is intercepted by surface 2. This itself becomes the irradiation if we just divide it. If we just divide this radiant energy leaving 1 incident on 2 divided by the total area of surface 2. And if that is done, you simply get what is the irradiation on surface 2 in this case. Okay, is this clear? Like, any questions on this? See, there are a couple of things in radiation that you need to keep in mind. First, when I say it's radiant energy, remember it's not the flux. This Q is not flux, it's energy. Okay, that's why it have an unit watt. But if I say irradiation or emissive power or something like that, it means it's a flux. So remember, this E1 is an emissive power, and this radiant energy is, you can see it's multiplied. So this emissive power, when multiplied with some area, gives you the radiant energy. So you can appreciate that your radiant energy indeed bears an unit of watt and not watt per meter square. Okay, so that also you need to keep in mind basically. So these are the things also, like, you need to understand. But when I say it's a radiant energy, always remember that it has to be a unit watt. Okay, and the other things like the irradiation, radiosity, and the emissive power, these bears in unit of watt per meter square, and that's why they are also sometimes called as radiation fluxes, as we saw previously. But yeah, this is basically the relation. Okay. So I hope this is clear. For instance, intensity of radiation has also got an unit of flux, because this has got an unit of watt. This has got an unit of what, meter square, and that's why this has to be an unit of meter square per watt per meter square to be precise. Okay, so intensity of radiation, emissive power, okay, radiosity, irradiation, all of these things are just fluxes. While the radiant energy, that when I say what is the radiant energy that leaves a particular surface is intercepted by another surface, this has got a unit of watt basically. Okay, and this is typically in general uh, how the spectral radiant energy is related to the spectral intensity of radiation in terms of the normal area and the solid angles basically. Okay. All right. So I hope you understood what we basically did in this problem. This was indeed it's kind of an indeed involved problem that we saw. So it's a good problem actually. We also understood what we meant by a diffuse emitter. And yeah, so this is something that we saw. Any questions on this? Okay. If no questions, I again thank you for actively participating in this discussion forum. I mean, in this discussion session. And so in the next class, what we will do is we will start off with something which is known as radiation from real surfaces. And then as you asked, and I mean, your question on this gray bodies would be much more clearer. Now we understood today what are diffuse bodies. Similarly, like we will also see what is gray bodies. And yes, I just give you a hint that for gray bodies, your properties are not a function. I mean, your radiation properties are not a function of wavelengths precisely. Okay, and that's the idea of a gray body. And there is something which is known as the Kirchhoff's law, as you have just rightly pointed out. And this is of course true for a gray body only. And we will see the implication of this Kirchhoff's law and the fact of how radiation heat transfer takes place from a real surface, and proceed into something which is known as the view factor analysis. And in fact, this discussion that we did today, that is this discussion on how the radiant energy emitted at the wavelength lambda is related to the intensity of radiation times all those things. This is the basic foundation of deriving something which is known as the radiation view factor basically. And if you see the derivation, this is from where people actually start and try to come out with the expression of view factor. View factor is just nothing but this quantity that we calculated, q1 to 2. Okay, so this q1 to 2 divided by some like total quantity is nothing but the fraction of energy that is emitted by one surface that falls onto other surface, and this fraction is just known as the view factor. Okay, and we'll see these things in basically in the next class. And yeah, so we I end this by something which is known as which is also known as this black body radiation. So there is also a term which is known as black body radiation. So actually there are some, so first of all, you need to understand that in nature, no body in any body, so there is no such body in this nature which are perfectly black bodies. It's like in thermodynamics we say that no efficiency can actually reach the efficiency of a Carnot. No efficiency of a heat engine can reach the efficiency of a Carnot engine. Similarly, like there are no such perfectly black bodies that arises at least in our world. But it's kind of an idealized concept. For instance, a black body, it's so there are certain properties of black bodies. Okay, first property is that like the emissivity of black body is basically equal to 1, which means if I say what is the emissive, now if I just say what is the emissive power of a black body, it just becomes equal to sigma times t raised to the power 4, typically because your emissivity is equal to 1. Also, for a black body, it is said that a black body absorbs all the radiation that is incident on it. Okay, so this is also one property of a black body, that it absorbs all the radiation that basically falls on it. Okay, and it is also said that at a given temperature, your black body has the maximum emissive power. That is again because of the fact that your emissivity of a black body is basically equal to 1. Okay, so these are some properties of a black body. So okay, so black body radiation is kind of an idealized radiation, and the radiations and the emissions from the other surfaces, that is from the real surfaces, are, are drawn. So they are studied with reference to a black body, basically. Okay, so that's the idea behind a black body. There is nothing such special about a black body. It's just that so you just need to keep in mind that at a given temperature, a black body emits the maximum. A black body has the maximum emissive power because of the fact that its emissivity is equal to 1. Also, a black body absorbs all the radiation that is incident on on its surface. Okay, and of course, a black body is also a diffuse emitter. That also you need to basically kind of understand this. Okay, so these are some properties of a black body. I think you have some questions on this in the in assignment 1, but these are very easy and you can just answer them with respect to them. Okay, so with this, okay, so with this, we will end the discussion on today. If you have any questions, you can ask, or else in the next class, we will look into the radiation from real surfaces and then we will proceed accordingly. I hope you have understood what we discussed in this class. Thank you very much for attending. If you have any questions, you can ask, or else we'll meet in the next week. And I'll try to come up with a good answer on the question that you asked today. That is on this on the fact that even if we have a same material, the radiation properties can indeed be different. Although, like I hinted about the fact that because your properties are also spectral and they show, directional properties and, spectral dependencies basically. Okay, so I mean, I'll I'll try to come up with a better answer in the next class if there exists, and we will see from them. Okay. Thank you very much for attending the session. If you have any questions, feel free to ask or you can just post it in the discussion forum of the group. Okay. All right. Thank you guys. Thank you very much for attending this session. We'll meet it in the next week at the usual time.